Hey folks, so second part of this series of waypoint control for a car. We are going to cascade this into three loops. The first loop is the velocity controller to maintain velocity. Then we're going to have a heading loop controller to steer to a certain heading. And then we're going to have a waypoint controller that is going to take XY coordinates and convert that to a heading command to send to the heading loop controller. Okay, so you can kind of decouple this and put your, heading angle controller here, and then up here you can put your throttle controller. Now this is the default throttle controller at 1400. I would rather have a throttle controller that had like a 1000 plus some what I'm going to call proportional gain times an error signal. So I'm going to just call it error signal. And then up here, I'm going to make my error signal equal to my U velocity minus my U command. And what's my U command? My U command is 10.0. I want to just travel at 10 meters per second. I think that's appropriate. Now U doesn't exist in this code. So I need to go up to here and grab the forward velocity down here and say, hey, these are my kinematics, and then throw that in there. Now, if you're building this for real and you're driving a car, how are you going to get the forward velocity? Typically, you use a GPS and you get your XY position, and then you take a derivative of that, and then you get your forward velocity. And so I'm assuming here, assuming that you are getting GPS data to obtain velocity. Okay, that's how you would do that in real life. Now, how do I make this KP? Well, for now, I'm just going to set KP to 1.0 and just see what happens. So I'm going to run this code. Now I've got delta throttle with a KP error code, and it says that my velocity is negative. Okay, what that means is, first, it's possible that there is a saturation issue here. So if I print delta throttle, come on, and hit play, it's 989, which is less than 1,000. So the first thing that needs to happen is I need to put a saturation controller in here and say if delta throttle is less than 1,000, delta throttle is equal to 1,000. And then not to mention, if delta throttle is greater than 2,000, make delta throttle equal to 2,000. And that way I add that saturation controller in there. Now, the other issue that's happening is that the car is actually traveling in the wrong direction, which means our proportional gain is the wrong sign. And so now if I flip it, you'll see that the car gets to 0.25. Now that's weird because I told it to go to 10. Now what's happening here is that there's a drag term on the vehicle. And so if you only use proportional control, even if I upgrade the gain, I'm going to add the gain in here. Even if you add that in, you're still not going to get up to 10. So if I make this like 1,000 and try again, 100, not 1,000, I still only get to this value right here. And then what I can do as well is I can go ahead and print delta throttle again. I'll just comment it out this time and run that to see what the value is hitting. It's hitting 1285. So it's not like it's hitting 2000 and hitting some sort of limit. What's happening is that there's a drag term that the controller doesn't know about. And so unfortunately you have to add what's called integral gain, and you typically want to make this small. So I'm going to make it 1.0. And then your error integral, because this is a fixed step integrator, what you can do is you can simply increment your error by some value. And so I'm going to make error a global variable, global error int, and then I'm going to initialize in this initial conditions my error int equals 0.0 and make it 0, and then that's to start off. And then here what I'm going to do is I'm going to say error int plus equals my error signal. And this only works because I'm using a fixed step integrator, and so I know it's incrementing by a little bit at a time, but basically what's happening is if there is error in my error signal between my velocity command and what I'm actually traveling at, that error int variable will increase over time, and then when I multiply it by this ki gain, that will close the gap. And so if I run this now, oops, I hit print on there. You can kind of see what's happening already. You probably saw it. Is there's a little bit of lag in the system because the car slows down, but then that integral gain catches up, and then we eventually hit that. And so how do we get rid of that little dip? We can make ki bigger, so we can make we can make kp bigger, like 120, and we can double the ki gain, and it will still dip a little bit because that's just how it works. But it definitely got back a little bit faster. So within 5 seconds, we're traveling pretty good. So I think this controller is working pretty well. Just to make sure that it's robust, I'm going to change the command to say 5 and then run it and just see if the car can compensate. And it looks like it does just fine. It rolls down a little bit and then settles out at 5 meters per second. Okay, so the velocity controller is done. I'm going to set this back to 10. And I'm going to, oops, I don't want to debug you. I'm going to run that and just make sure that I have the velocity controller running. And so now we're at a good speed of 10 meters per second, okay? So now we go back to our control term, and it's time to make our heading angle controller. So for now, I'm going to make my heading command equal to 45 and p.pi over 180.0. And then what I need to do is exactly the same thing. Delta steer. I already have delta steer down here. You have the 1500, right? Because you are driving center, right? I don't know if you noticed down here, like I added this 1000, and that was because you want your nominal value to be 1000 and then your KP signal to be, up or down to that. You could make the delta throttle signal 1500, but then that would mess with your KP and your error signal. And so I like just using the baseline. But the baseline for the steering is just 1500. And so I'm going to add another KP, but I'm going to call this like a KPP for like KP psi. And then I don't anticipate using any integral gain on this one because there is no, the drag term is on the yaw rate, and we're just worried about the heading. And so there will be steady state error in our yaw rate command, but we'll eventually get to our heading command anyway. So I'm just going to do psi minus, I guess I'll do psi command to stay consistent and call this psi command. And then add, nope, don't need to add anything. I just need to make a KPP and make that say 1.0. And so now our car should drive at 10 meters per second and turn to 45 degrees if we have the gains set up properly. And we don't. It's going off negative. It's going in the wrong direction. The vehicle is steering the wrong way. And so I need to put a -1 in there, run it again, and hopefully the vehicle will travel to 45 degrees. It doesn't look like it quite gets there. Here's the yaw rate right here. We could also probably plot the heading. So let's go ahead and add that in. plt.figure, plt.plot,tout, psi out. I think I have psi out already defined. It's right there. Let's make this a little bit easier to understand and multiply by 180 over pi. Make a grid, and then let's make an X label with just T, and then a Y label of heading in degrees, okay? And so let's see if it even gets there in the 20 seconds. And you'll notice it's barely even steering. So we need to make that value bigger. Now, if you think about it, 45 times pi over 180 is 0.707, I think. Let me check that real quick. No, because 1 radian, yeah, it's like 0.5, I think. NP dot pi over 180. Oh, there is no NP. So let's just do 3.141. Okay, so it's 0.785. So I was 707, I was close. So this is like 0.7. If my heading command is 0.7 and I multiply by 1, I'm only doing a 1 PWM signal. But really, like, if I'm off by 180 degrees, I'd like it to be 500. And so I think what I'm going to do is I'm going to make KP negative 500 over 180. So if my heading command is 180 degrees, I will do a command of 500. And 500 over 180 is like 2.7. Okay? So let's give that a go and see if it steers much faster. You know, it's possible. What is my, let's check what my PWM command is, if that makes sense. Let's down here print delta throttle. Let's also print delta steer, and let's see if we're actually applying enough control. So yeah, we're only doing 1501, so I must have done the math wrong. What's going on here? Oh, this is in degrees. That's the problem. So this needs to be not over 180, but pi, which I can just do np.pi. So 500 over pi, 3.141, is like 160. Okay, that's a way bigger gain than I had before. Okay, now let's try it. So throw that in there. Yeah, my PWM signal is definitely, that definitely looks like 45 degrees. And there's my yaw rate, which looks really cool. And then bam. So like in 5 seconds, we get to 45 degrees. No problem. I might even increase that gain a little bit. It was like 500 over pi. I might double it so it's like really fast. It will saturate. So we need to put another saturation in here. If delta steer is greater than 2000, right? Delta steer is 2000, and if delta steer is less than 1000, delta steer is 1000. And so that way we can increase the gain by a factor of 2, and we don't have to worry about saturating the controller. I still have that print statement in there. My apologies. Let's comment out that print statement and then run the code again. And then now we will hopefully have the vehicle travel to the desired heading. Velocity controller is working. Because we increased the gain by a factor of 2, we are getting some oscillations in there. And so the gain does overshoot. And so we could lower it a little bit. But again, this is just for, educational purposes. We're not actually going to build this. And so let's just leave it like that. So there's a little bit of overshoot, but it doesn't seem like it's a big deal. Okay. All right, so we got our heading controller working. Now, here is the problem. Let's say I'm traveling at 5 degrees. So I guess in your case, this would be this way, right? Yeah, this way. So you're traveling at 5 degrees that way. And you want to travel this way. This is 350 degrees. And if you do 350 minus 5, you're going to get an error of 345, and the vehicle is going to turn all the way around to travel when it really just needed to close the gap. Okay? So this error of psi minus psi command is not robust enough to handle the fact that your heading can go from 0 to 360, and when you go past 360, you don't go to 361, you go back to 0. And so what you need to do is you need to get the angle between two vectors, and if you do a dot product between two vectors and divide by the magnitude, you get the cosine of that angle. And so there is this function here called del psi, and what you need to do is, looks like this is in libraries math cp.cpp, and here is del psi right here. And so what we're going to do, returns delta psi from a heading and a heading command without worrying about wrapping issues, which is where you wrap around 0 to 360. And so I'm just going to copy this whole thing. It's in C++, but we will take care of that when we put it in Python. And so I'm actually going to, I guess I'll paste that code into here, and then I'm going to grab my kinematics and, oops, there we go. I'm going to grab my kinematics, Control X, and I'm going to put that up here, and then I'm going to compute a heading error using non-wrapping function. Sure. And I'm going to go ahead and leave these comments in here. Returns delta psi from a heading without worrying about this. And this computes delta psi is psi minus psi command, and I put by the way. I'm going to get rid of that by the way. And if you notice down here, this is psi minus psi command. And so what we do is we replace this with del psi, and then what we do is we make sure this code works. So in C++, you have to declare variables, so you have to tell it that it's a double. In Python, you don't need to declare that it's a double because it defaults to a double. So we can just delete that, delete that, delete that. Then our output variable is going to be del psi, not out what it was out before. And then all of these functions are np dot, np dot, np dot, np dot, or np dot, and then I think it's actually arctan2 in C++, or sorry, in Python, and you don't need that semicolon. And so the code will run no problem, except that psi c doesn't exist, and that's because this variable needs to get moved up to here. And I'm going to change psi command to psi c, and then run that, and then the code will hopefully output exactly the same exactly the same thing, but the wrapping issue has been solved. So you have to make sure that you add that in. Otherwise, if you are straddling that 0 to 360 mark where you're traveling north and the heading is flopping from 360 to 0, your car will end up traveling the wrong way just to get to the desired heading, which is no good. Okay, we're almost 20 minutes in, and it is now time to add the waypoint controller. Okay, so what we need to do is connect the waypoint controller to the heading angle controller. And so if you go, I mean, you can go, all of this code, by the way, is in here. This heading loop controller, you can see that I have this del psi in there, and I basically have the same thing where I have like an integral in the heading. Okay, so that's interesting. So I do have an integral in the heading here, and then I also have a KP on the heading. The waypoint controller, all we're going to do is get the difference between our waypoint command and where we are, and then just create a heading command using an arctan function. And so it's very, very simple. We're going to, up here, we're going to create a waypoint. And so first, let's run this simulation without this waypoint, and let's see where the vehicle travels. So the vehicle travels pretty close to 100 by 100. So let's see if we can get the vehicle to get to 100, 100. Okay? So what we're going to do is we're going to do a X waypoint is 100.0, and our Y waypoint is 100.0, and then we're going to get a DX is, according to this code, is going to be the waypoint minus the value. So that's going to be X, right? That's part of our state vector. And again, you would need GPS to get your X coordinate minus your X waypoint. And then dy is Y minus your Y waypoint. And then your heading command, so I'm going to comment this out, psi c, and I'm just going to do psi c up here, is going to be equal to np.arctan2 of dy, comma, dx. And that will hopefully connect the fact that the car needs to go to that 100, 100 waypoint, and it looks like it went the wrong way. Okay, so what does that mean? It means we need to put a negative sign here and try again. And it still went in the wrong direction. Okay, so, I think we might need to draw a picture. So I'm going to pause. I'm going to make sure I don't end the video this time. And I'm going to draw a picture, and we're going to see what exactly is going on. Okay, folks, I drew a picture, and then I found the issue. So right here, I'm going to draw a square. This is where my car is at 0, 0, and it's traveling this way. So, I mean, I could draw, I guess, an arrow on this, but I don't want to. Anyway, so it's traveling to the right, and again, the heading is this way, right? So if I put 100, 100, if my waypoint's up here at 100, 100, the heading angle command should be 45. And so what's happening is that you need to get your dy and your dx, and you're going to do arctan 2 of dy over dx. But what I didn't realize is that you need to do the waypoint minus your current position. And so I went back to the code and I changed that. X waypoint minus x, y waypoint minus y. I just had to swap those. And then when I print the sci command, I printed that just to make sure that I got it right. I got a heading command of 45. And so now if I plot it, you'll see that the vehicle turns to 45. There's a little bit of overshoot you can see right there. And then it hits 100, 100 perfectly, and then it starts to steer around. If you look at the velocity again, there's like a little bit of drift here. And then when it passes the waypoint, it does a harsh turn, and it starts to skid as it goes around that turn. And so you can see that yaw rate right there because it's basically doing like 180. And then there's the heading going crazy. And so what's neat is if I run the simulation longer, right? So if I do, say, 100 seconds, not 1,000, 100 seconds, and I run that, what will happen is that the vehicle's just like, just like driving around in circles. Now, it should be a perfect circle. It's probably numerical precision. I could lower the time step, but I don't really want to. But it's basically just circling around this, okay? And you can see the yaw rate just going nuts. And then it looks like it eventually hits steady state, and the heading angle is just like blowing up to infinity, right? Which is because it's just circling around in circles. And you notice there's no wrapping issue, right? Now this isn't very cool, right? What I'd rather do is make like an array of waypoints and just have it travel between those waypoints. And so what I'd like to have is like x waypoints with an s, and then y waypoints with an s, and then like a waypoint counter, right? And so what I'd like to do is have the x waypoint be the x waypoints of the waypoint counter, and then the I got to do square brackets because we're going to make an array, and then y waypoints is y waypoints of the waypoint counter. Now, what I'd like to do though is put some sort of statement in here that says, hey, compute the norm between u and the waypoint. So let's do np square root of dx squared plus dy squared. And what I'd like to do is say if the norm is less than like 10 meters, 3 meters, I want you to increase the waypoint counter. But if the waypoint counter is greater than the length of the waypoints, I want you to set the waypoint counter back to 0. And then what we'll do is down here at the beginning of the code is we will, in the initial conditions, we will create x waypoints. And what I'm going to do is I'm going to do np array. I'm going to do 100. I want to do a square pattern. So 100, 100, 0, 0. And then the y waypoints are going to be 0, 0, 0, 100, 100. And then we're going to initialize the waypoint counter to 0. Now, if I did this perfectly, which this never happens, so if it happens, I'm going to be excited, the car will drive a perfect square pattern over and over and over again. Dang. Okay, index is out of 4. I told you, never happens. I think what happened is I said if the waypoint counter is greater than, I think I need to say equal to, and then try this again. Oof. It looks like it's switched from these two. What am I missing? So what we need to do is every time the waypoint, so let's put this, I would say every time the waypoint switches, we should print arrived at waypoint, right? And then we'll do x waypoint, y waypoint, and then hit play. So it's going to 100, 0, and then, oh, we have a problem here. The RK4 engine is running the derivatives routine 4 times but the control loop can only run once per integration time step, which means we need to pull out this control routine, send the control variables delta steer and delta throttle as inputs to the derivatives routine, have the control routine return, that's fine, but we need to run it only once, run control loop once per time step. This wouldn't happen in real life, but it's happening in simulation. And we need to give it the time and the state vector, which is state 0. It's going to return delta steer and delta throttle, and then the derivatives routine needs to get augmented with delta steer and delta throttle because those are constant throughout the RK4 function calls. And now if I run it, that looks a lot better. Dang. Okay, that wasn't it. I could have sworn we made it. Okay, so arrive at waypoint 100 0. Let's spit out the time too. Let's see what's going on here. So if I spit out t equals and type in t like that, and then run it. Yeah, see, it's arriving at the waypoint too quickly because it's not. Did I make the waypoint counter a global variable? I did. And so if the norm is less than 3, the waypoint counter plus equals 1. And so let's spit out what the waypoint counter. Let's spit out what the waypoint counter is. So waypoint counter equals. So somehow it's running the control loop twice, but I commented that out. It should only run that once, and once the waypoint moves to 1, unless I have the waypoint bad. Oh, it's 100 100 0 0. Okay, I missed. That's what happened. So the x coordinate needs to be 0 100 100. Yeah, okay, so it's 0 100 100 0, and then the y coordinate is 0 0 100 100. There we go. Okay, so let's run that real quick. And there we go. That looks great. Well, it kind of looks great. What's happening is that the car is going straight. It hits this waypoint. Drives past it. Circles around, hits that waypoint. Drives past it. Circles around, drives past it. Circles around, drives past it. How would you make this better? I mean, you'd have to have like a model predictive controller to like not hit the waypoint and start to turn early. You could have the car like slow down as it's approaching the waypoint and things like that. But I think for the most part, the algorithm is there, and I think I've overstayed my welcome. We've got a 30-minute video here and a simulation that you can play with and run your waypoint controller. And so if you have any questions, post in the comments. I will post the link to this code in the description of the video. And I hope you have a great day, and I'll see you in the next video.